Okay, so if you recall from last week, we were looking at the simplest class of partial differential equations to solve, and these are elliptic PDEs. Okay, and then one of the reasons why elliptic PDEs is so simple to solve is they don't have the time derivative. Okay, so elliptic PDEs are only expressed in terms of the spatial variables x, y, and z if you have it. Okay, so that means the solutions to elliptic PDEs don't change over time. So once you have a solution, that solution is what we call a steady state solution. Okay, so it doesn't then evolve. We'll look at, next week, we'll start looking at what we call hyperbolic PDEs, which they model systems which change over time, which is slightly more complicated. Okay, last week we looked at the idea of a two-dimensional finite difference grid. Okay, so, and in particular we looked at Laplace's equation. Okay, with all types of finite difference methods, what we do is we take the domain, which is kind of the region which we're having, the region for which we're trying to solve for, and we discretize it. What that means is we don't solve for all of the domain, we solve for specific points. And these given by these black dots here. These points are called finite difference nodes. Now with the finite difference method, those nodes have to be placed in a uniform grid. So you'll notice we have like this sort of rectangular grid type structure. That can give problems if we've got a complicated domain. That's not always the best way to represent it. And in term 2, after Christmas, you'll be looking at a method called finite volume methods, which can do, which are much better at discretizing a complicated or a complicated shape domain. Okay, but for now we're looking at finite difference grid. So here we have 2D. So x is traditionally represented as a horizontal axis, y as a vertical axis. And what we have is we have these, what we call indexes. Okay, so I refers to the location of the finite difference node along the x direction, and j refers to the location along the y direction. Okay, so as we go from left to right, we're increasing our I index by 1 each time. And as we go bottom to top, we're increasing our j index also by 1. Okay, and delta x is the spacing between nodes in the x direction, delta y similar to the y direction. Notice delta x and delta y don't have to be the same. Okay? They can be different. Okay, and this is what we looked at last week, Laplace's equation, perhaps the simplest, most common example of an elliptic PDE. So it's a double derivative of u with respect to x plus a double derivative of u with respect to y. And using second order symmetric differences, so these differences here, they're taken from the finite difference toolkit. Okay, they're all derived from Taylor series. In practice, we don't derive them each time, we just look them up. Okay, so if I take the finite difference in the x direction, okay, notice the j indices, they don't change. Because remember, y is fixed in partial derivative, we're taking the partial derivative of x. Okay, so this first fraction is the finite difference approximation of uxx, and the second fraction is the finite difference approximation of uyy. Okay, and notice in the second one, it's I that's fixed, and it's j which we alter. What you're actually trying to do here, so we've gone from a PDE, partial differential equation, to an algebraic equation. And what we want to do is we want to know what's happening at this node here, uij. That's our current node, that's the node we're trying to solve for. So if I rearrange to make uij the subject, we get this on the right-hand side. We can simplify that further if we choose to have the delta x and delta y being the same. So that means the same spatial difference in the x and y direction. We end up with that. Okay, so essentially what this means is that our solution for node ij is equal to the sum of the nodes to the north, east, south, and west. Add them all up, divide by 4. That's our solution. Okay, so that's our finite difference scheme for Laplace's equation. This is second order accurate because we've used second order differences here. If I use fourth order, okay, we'd have lots more nodes. We'd have a different finite difference scheme. Okay, we looked at this sort of simplified example. So here I've got a two-dimensional domain, and I've got 5 nodes along the x direction and 4 nodes in the y direction. And notice the node numbering convention here. Okay, so the first number in the subscript, that relates to its position along the x direction, the second number position along the y direction. And by convention, we start at zeros. So 0 on this node, or these nodes here on the left, they mean, okay, that's our first nodes on the left. And likewise on the bottom, we start with 0, the second index, and work up. Right, and we looked at the Jacobi method. Okay, so we want to solve this equation. Okay, there are 2 main types of methods to solving algebraic equations: direct and indirect. Direct methods are okay, but they're very inefficient for large systems. So we choose to have an indirect method. And the Jacobi is the simplest version. Okay, and all we do is we start with an estimate of the solution, and we improve on that estimate and keep doing that over and over again until we've got a solution we're happy that it's accurate enough. Okay, so here I'm going to introduce a notation where we've got a superscript k, and k is essentially the iteration. So all of the superscript k on the right-hand side here, we know what those values are. Okay, so we start off with some guess. So when k is 0, we choose a guess value, normally 0. And our better guess, our improved guess, is just calculated using that equation there. And we keep going until we're satisfied with the accuracy. And we saw last week that this particular problem took 33 iterations. Okay, so here are my computational nodes. I started off with a guess of zeros. I kept doing the same calculation, this calculation here, over and over again. And eventually, after 33 iterations, what we have is what is the difference between our new guess value minus our old guess value, and we calculate some error. Okay, and as soon as the error was less than 10 to the minus 6, I stopped iterations. And that's where we left it last week. Okay, this week we're going to be looking at 3 other indirect methods. And the first one's called the Gauss-Seidel method. Okay, and the Gauss-Seidel is kind of like an obvious improvement over the Jacobi method. Now, the problem with the Jacobi method is we're not using the most up-to-date information at each iteration. So here it is. Okay, here's my Jacobi method. Now, if we calculate the solution for one node, and then we move to the next node to the right, and then calculate that one, the node on the left has got an updated estimate. Okay, so for example, if we're calculating ij, okay, and we're going from left to right, bottom to top, the node ij minus 1, we've already updated for the current iteration. And this node here, I minus 1j, we've already calculated for the current iteration. Now, in the Jacobi method, we're still using their old values. Okay, well, that's inefficient. Why not use the most up-to-date information? And that's essentially what the Gauss-Seidel method does. Okay, so what it does is if we use row by column order, which means we're going across the row, so we just start at the bottom row, go across, and we move up a row, and then go across again. The nodes to the west, i.e. the left, and the south, i.e. bottom, are already known, already been updated. So why not use them? So essentially, the Gauss-Seidel method is written like this. So we have on the right-hand side some k+1 superscripts. So that denotes for the current iteration, we've already calculated updated values of these, so use them. Why not use them straight away? Oops. Okay, so if we go step through some calculations, starting with 0 guess values. So the first one is exactly the same as the Jacobi method. Okay, so add up blue nodes, divide by 4, and we get 3.5. This red node will be equal to 3.5. Now, if we go across, we do exactly the same, add up the 4 nodes, but this one, okay, has already been updated, so why not use it? In the Jacobi method, we would have used its previous value, which was 0. Because it's already been updated, we use it. And likewise with the third one. Okay, so add up the blue nodes, this one to the left. Okay, in the Jacobi method, we would have used 0, because it's Gauss-Seidel method. We've already calculated for the current iteration, so we update. Okay, and we do that using row by column order. And at the end of the first iteration, those are the values. Okay. By the way, the size of these circles, it doesn't mean anything. It's just so I could fit the numbers on. So just because they're bigger circles doesn't have any doesn't make any difference. Okay, so that's the first iteration of Gauss-Seidel method. Second iteration, exactly the same. Step through, always using the most up-to-date information each time. Okay, so a bit of number crunching. And at the end of the second iteration, those are our values. Okay, so of course we have to go through quite a few more iterations before we get a solution. And it's 18 in this case, to be precise. So after 18 iterations, we say, okay, our error is less than 10 to the minus 6, so we stop. And so that took 18 iterations. The Jacobi method for the same problem took 33. So we've almost halved the number of work, or the amount of work we have to do. Okay, so last week we had to go at a worked example. So this week's I want to do similar, and this is on page 51. Right. Okay, so this is on page 51 onwards. Okay, we have a very simplified sort of problem. I'm calculating Poisson's equation this time, very, very similar to Laplace's equation, except that instead of equal to 0, we've got equals to some function. In this case, it's x plus y. And I've just got 4 computational nodes in the middle, which I'm going to be solving for. And we looked at last week. Okay, so given Poisson's equation, we derived the finite difference method, which is essentially this one down here. There was a quarter of the northeast southwest node minus 1/9 times the coordinates of whatever the current node is added together. Okay, and as you can see, I got a bit bored halfway through, if you recall. That was the Jacobi method. Okay, now we're going to do the same for Gauss-Seidel. Okay. So all we do with Gauss-Seidel, okay, is calculate the value of the ith node is essentially exactly the same as the Jacobi method, except for the nodes to the south and to the west. We use a k+1 So we have a quarter. Okay, so that's a node to the north, so we still have to use the old value. That's the node to the east. Again, we use the old value. But the node to the south, we can use the most up-to-date value, which is the k plus 1. And also the node to the west, use the k plus 1 value. Okay, so that's our Gauss-Seidel method. Right, so now we've got to do the number crunching. So starting with 0 starting value. Remember, it doesn't matter what starting value you use because it's a steady state solution. You're always going to get to the same solution in the end. Okay. I use 0 just because it's easy. And I'm going to be incredibly lazy now. Okay, the first calculation for the Gauss-Seidel method is exactly the same as Jacobi. So why do the work again? I've already done it up here. So our first value, 731481. Sorry. So now I'm going to calculate node 21, which is going 1 across. Okay, so a bit of number crunching. So what we have is we have a quarter multiplied by the node to the top, which is going to be U12, which is 0. I'm going to type 0. I know you don't need to do it, but I'm just going to do it. Plus the node to the east, which is also 0. Plus the node to the south, which was 1. Plus the node to the west, which is that one there. Yeah. So the node to the west, which is our new value, 0.731481, and that's minus 1/9 times 1/3 plus 2/3, which was 1. Okay, so I'm just going to flip over just to the. So I've just calculated this node. So it's that node plus that plus that plus the new version. Okay. Well, the x-coordinate of that node is 2/3. Okay, because this is x equals 0. That's x equals 1. That's 1/3. That's 2/3. The y-coordinate is 1/3. So 2/3 plus 1/3, which is obviously 1. Okay, and it's given us 0.405092. Okay, do the same with the node U12, which is this node. So take 3, add 3, add U11, which is new, and U22, which is old. So notice I'm using that new value there. Okay, and we get 1.655092. Okay, U22 would be 0.25 plus the boundary nodes of 1 and 2. So that's 1 and 2 there. U21 and U12 have already been calculated here. So I'm using the new values, which is 0.405092, that's 1.655092, plus 1/9 times 4/3, because the x-coordinate is 2/3, the y-coordinate is 2/3, add them together, it's 4/3. Okay. 1.3. Oh, yeah, 1.302083. Excuse the writing there, terrible. Uh, 2083. Okay. Have to calculate the error. What we do with the error is we subtract each of these from the one above, square it, add them all together, square root. Okay. So it's finding the magnitude of the difference between those two vectors. Okay, so I'm going to get my calculator out again. So I've got 0.731, 481. Well, that's going to be minus by 0, so I don't have to do that. Squared plus 405, 092 squared, that's 1.655092 squared, that's 1.30. Oh, done it again. 30201. So 083 squared. 3.65. 3.2658, blah blah blah. Okay. So, and you keep going. Okay, it's not going to surprise you, but I'm going to leave this for you to finish off. Okay, so what I want you to do is finish off these first 4 iterations in your own time. You don't want to see me just sort of type them into the calculator. Yeah.
You subtract the first one from the 0 1.
Sorry?
You subtract the first iteration from the
yeah.
starting one. Then
for this error. So,
yeah.
Yeah. So what I've done is I show you that minus that, that minus that, that minus that, that minus that, square them, add them together, and then square root them. So that's essentially what I'm doing is I'm calculating what's the magnitude of the vector of this vector minus that vector. And that gives us the absolute error. Okay, in short, the Gauss-Seidel method is much more efficient than the Jacobi method. Okay. It can be tedious, especially if you're doing it by hand. That's why we don't do things by hand. We use a computer. Right, that's Gauss-Seidel method. It's more efficient than Jacobi method. Brilliant. We can go home. I'm afraid not, because we've still got a bit more time in the lecture. We can also improve over the Gauss-Seidel method. And this is the idea of what we call the successive over relaxation, or SOR method. Okay, and what we do is we update our solution using a weighted sum of the current value, the K value, and the solution via the Gauss-Seidel method. Okay, so what I mean by that is, okay, if R, that's the difference between 2 successive iterations. So therefore, if our next value is equal to our current value plus whatever that difference is. Now, if I apply a weighting to R, okay, and I'm going to say let omega, this is the lower Greek character omega, I'm going to say let omega be a weighting, I just multiply our difference by that omega. Now, if omega is less than 1, I'm reducing R. Okay, I'm reducing the difference. If omega is greater than 1, I'm increasing that difference. Okay, so it's kind of omega. We choose to be. It'll be different for each problem. We choose the best one, which will give us the best convergence. And omega is called a relaxation parameter. Okay, and omega has any value in the range 0 to 2. Okay. And that's what we set. We choose omega so that it's best for our problem under consideration. So when omega is less than 1, the difference between successive iterations is reduced. Why would we want to reduce it? In certain cases, I'm going to do a bit of a sketch on the visualizer here. Okay, along the bottom, this is going to be my equations. And let's say this dashed line is my solution. Okay, sometimes, if we apply indirect methods, what it does is it bounces about the solution like that. And eventually it will sort of converge on the dotted line. Okay, so this is our first estimate. Here's my second estimate. So you can see the difference has sort of overshot the solution. So if I was to somehow reduce that difference, it would converge to the solution quicker. Okay, so what I'm doing is I'm updating it too much. I'm overshooting each time, and it's oscillating about the solution. So if that happens, we should use omega. We should use omega, which is less than 1. Okay, that would help improve our convergence. However, when omega is greater than 1, okay, the difference between successive iterations is increased. And this is called over relaxation. Okay, so if I go back to my diagram, so again, this is iterations. Here's my solution. Let's say I'm starting here, and then my next estimate is there, then my next one's there, and it's getting closer and closer to the solution. Well, I can speed that up by increasing that difference. So instead of that difference being there, I could have had it down there, and that would increase the speed of convergence. Okay, so sometimes you want to choose omega when it's less than 1. Sometimes you want to choose omega when it's greater than 1. Okay, so this, when it's greater than 1, it's used when the method converges to the solution atomically. In other words, it never goes away from the solution, it always goes towards it. When omega is equal to 1, we just end up with our standard Jacobi or Gauss-Seidel method. Okay. And the optimum value of omega will purely depend upon the problem we have. It'll be different for each different problem. Okay, so what we have here is this is our Gauss-Seidel solution. Okay, we just did this just now. And one thing I'm going to do is I'm going to take out Uij here. I'm going to add it here, but I'm going to take away the same thing there. So what I've done is to the right-hand side, I've added Uij, okay? But I've also taken it away there. So I haven't changed the formula, just added something and taken it away. Okay. Well, this is my R, because that's my current estimate. So therefore, that must be the difference between my current and my next estimate. Okay, so that's my R. And if we multiply R by omega, we get this. Okay. So we have 1 minus omega times our current estimate plus omega times our Gauss-Seidel solution. So when omega is 1, 1 minus 1 is 0. So that totally disappears. Omega is 1, and therefore we just got Gauss-Seidel. Let's say omega is less than 1. If omega is less than 1, okay, so we've got a little bit. So let's say omega is a half. We'd have a half times our current estimate plus a half times our Gauss-Seidel estimate. What if omega is 1.5? We'd have minus a half times our current estimate plus 1.5 times our Gauss-Seidel estimate. So that value of omega is used to sort of tune it. It's used to sort of speed it up a bit. And that's the SOR method. Okay, so the bit in brackets is, this bit in brackets here is the Gauss-Seidel method. Okay, so it's often written like this: 1 minus omega times our current estimate plus omega times U bar. U bar is just whatever your Gauss-Seidel is. And this is more accurately known as the point SOR method. The reason being is we take each point at a time. Okay, so a few example calculations. Okay, so that first one is exactly the same as the Gauss-Seidel because we've got a 0 starting value. Okay, so here I'm choosing omega as being 1.0975. That happens to be the optimum. Okay, I'll tell you about how I calculated that in a minute. Okay, so we've got 1 minus 1.0975 here, and that's times the current value plus 1.0975 multiplied by our standard Gauss-Seidel formula. Okay, and keep going down. It's exactly the same way. Okay, and that's our first iterations done. Exactly the same way. We just got a slightly more involved iteration method. Do the same thing again. Cycle through the calculations. And there we go. Okay, so that's after 2 iterations. If we have a look to iterate until convergence, this is the same problem before. It took 33 iterations with the Jacobi method. It took 18 with Gauss-Seidel. It's only taken 13 with SOR without omega. With different values of omega, we'd have different convergence rates. That happens to be the optimum. I could choose a really bad choice of omega, which would increase the amount of work I have to do. Okay, so omega is, it's useful to be able to know what's the best one, or what's the optimum value. Okay, we could go through the worked example. Actually, I'll do it for a couple. I won't do it as much as I did before, but let's have a look at the worked example again. Okay, that's page 51. Tilt the camera down a bit. Okay, so if you have a look at the bottom, I'm back on page 51, I've suggested an omega of 1.1. Okay, so if I was to write out my SOR scheme, okay, we have 1 minus omega times the current estimate. So our omega is 1.1, so we have minus 0.1 times our current estimate, Uijk. We'd have plus 1.1 times a Gauss-Seidel solution up here. It's exactly the same as the Gauss-Seidel. Okay, so the first one, the boundary values were 1 and 2. Okay, so we have the minus 0.1 times the current value, well, that's just going to be 0, plus 1.1 over 4 multiplied, okay, so it's going to be 1 plus, well, c plus 1 plus 0 plus 0 minus 1/9 times 2/3. It's very, very similar to the earlier calculations. So in this one, we get 804,630. We round to 6 decimal places. Okay. So notice with the Gauss-Seidel, our first value is 0.73. Okay, so immediately we've got a different one. Okay, if we do the same for the others, just have a look at the boundary, 1, 1. Okay, so we have, it's going to be 0 times 0.1, so I'm not going to bother with that. So we've got 1.1 over 4 times 1 plus 1, which is the boundary, plus 0 times that one. So I've just calculated it. 0, and then that's going to be minus 1/9 times 1. So that's 0.740718. And if I continue across the row, I mean, it's 3 plus 3, plus 0, but plus this one again. Okay, the reason why it's plus that one, so I'm here, okay, that one's 0, so that one I've already calculated. Which is 0.804630 minus 1/9. Okay, and U22 1.1 over 4 times 2 plus 1 plus this node, sorry, this one, that's the node to the south, plus this node, so it's the node to the west. And that's minus 1/9 times 4 over 3. Okay. I'm not going to bother with the error. If you want to calculate that, you can in your own time, but just the speed. I wanted to go on to calculate this one here, okay, because this value will no longer be 1. Sorry, no longer be 0. So this one here is minus 0.1 times that current value. Plus 1.1 over 4 times, okay, the boundary values are 1 and 2, plus the node to the west, sorry, the node to the east, which is 0.740718, that's the node to the north. Minus 1/9 times 2/3. Okay, 1.434062, exactly. Okay, do you understand that we're actually taking away a bit of our previous estimate, but adding on more of our new estimate? Okay, I'm not going to go through all those calculations. It's fairly tedious watching me type numbers into a calculator, I imagine. Okay, so that's SOR method. So as I mentioned, for this example, only took 13. Gauss-Seidel took 18. So we cut down on the amount of work we've done. Okay, we can improve on this further. Okay, so Jacobi is rubbish. No one ever uses it. Gauss-Seidel is better, but we can improve on the Gauss-Seidel with the SOR. What we have with line SOR is an improvement still. Now what this is, point SOR took each node and calculated each node at a time. What line SOR does, it takes a row of nodes and solves for the whole row at a time. So rather than taking each individual point along a row, it just takes a whole row. Now the reason why we do this is because when the SOR is written as a line SOR, we have what we call a tridiagonal system. that means we have a system of equations, a linear system, where if we look at the coefficient matrix, the main diagonal has non-zero values, and so do the upper and lower diagonals. Now, we can solve tridiagonal systems very efficiently as a method which hasn't been improved upon, which can solve these really, really efficiently. If the number of nodes in the x direction is greater than the number of nodes in the y direction, we go across the rows. If, however, the number of nodes in the y direction is greater than the number of nodes in the x direction, we take whole columns at a time. So it depends whether what your size of your grid is. If there's more nodes in the x direction, we solve across the row. If there's more nodes in the y direction, we solve down the columns. Okay. Tridiagonal systems can be solved very efficiently using what we call the Thomas algorithm. Now this is a bit, I'll come back to the Thomas algorithm in a minute. Okay, so this is what I mean in a diagrammatical sense. Here's our sort of finite difference grid. The red nodes are what we're solving for. So here we've got 5 nodes, and I solve for all 5 at once using one application of the Thomas algorithm. And then we solve for the next row all at once. We have a solution. And then we solve for the last row all at once. Okay, so that's what's happening when we're using the line SOR method. Okay. If, let's say we're concentrating on this node here, well, actually, we're concentrating on this row of nodes here. Okay. I'm assuming I've already calculated this row at the bottom. Okay, so I'm on my k plus 1 value there. So I've already done all the nodes on the bottom. On this one here, I'm saying, okay, well, this is what I'm trying to solve for at the moment. So I'm solving for the k plus 1 values there at the moment. But this row up here, I haven't got to yet. So that's still the old k values. With that in mind, we derive our line SOR method. So in other words, the nodes to the north, we have to use previous values. The nodes on the same row are what we're calculating, and the nodes to the south, we can use updated values. Okay, so in other words, we have this. This is our point SOR method. But what we have here is this node here, okay, which is the node to the east. In the normal sort of point SOR method, this superscript here would be a k. But because we're taking a whole row at a time, it's going to be a k plus 1. Okay. And what we do is we put all of what we're trying to solve for on the left and what we know the values for on the right. Okay, so this is just this equation rearranged so that we have the current j row on the left, so that's what we're solving for, and all these on the right are known values. Okay, we know what they are. So this one here is in the row below. Okay, and these two are old values. This is tridiagonal. The reason it's tridiagonal is because we have 3 terms on the left-hand side. Okay, so writing out that method for all nodes in our row. So what I mean by that is here I've got 5 nodes per row. So I have 5 equations. Okay, so imagine there's 5 equations there. Okay, so that's my line SOR method for all those 5 equations. Now we've got a problem here. This node is a boundary node. And so is this node, where is it? This node down here is also a boundary node. Oh, sorry, not that node, this one. So the 2 ones in red are boundary nodes because I is equal to 0 or I is equal to n. So we want to remove those from our calculation. We already know what their values are. So what we do is we take those red ones and put them over the other side. Okay, because these are known values. Now what I've got now is I have If I had 5 equations in my row, I've got 5 equations and I've got 5 unknowns. So all of these u's on the left are all unknown to me. Everything on the right, I know what the value is. Okay, so we have a linear system which we can solve. Okay, other way to write it is in that form. So I mentioned it was tridiagonal, so our coefficient matrix falls on the main diagonal minus omegas on the lower and upper diagonal elements. Okay. Here, just to shorten things a bit, I've represented D as this, which is what our known values are. Okay, so we have a tridiagonal linear system. And I mentioned before, we can solve that very efficiently. And the way we solve it is using Thomas algorithm. Okay. So essentially, the Thomas algorithm, given this type of system, okay, we label the lower diagonal nodes as A, the main diagonal nodes we label as B, and the upper diagonal nodes we label as C. Okay, and the ones on the right-hand side are D. So bear that in mind. So A is lower diagonal, B is main diagonal, C is upper diagonal. And what we do is we change the values of C and D. So what we do is for each row of our matrix, for the first row, we change the value of C so it's Ci over Bi. So if I go back a sec, so on our first row, we change this value of C so it's C1 over B1. For all other rows, we change our values to C using that expression. And we do the same for D. So we change the values of C and we change the values of D. Now what that results in is this. It results in a coefficient matrix with 1s on the main diagonal, our changed values of C on the upper diagonal, and our changed values of D on the right-hand side. This is dead easy to solve for. So if you see at the bottom, what this bottom row says is 1 times xn equals d dash n. So xn must equal to d dash n. If I go back a row, okay, what this means is d dash n minus this number times that number equals xn. So we can go back substitution. So similar to, if you recall how we did it, how you do it like Gaussian elimination, okay, we can go back substitution. And that gives us our solution to a tridiagonal system of equations. And this is sort of slightly outside the remit of this unit. Okay, I won't ask you to code this up, I won't ask you to use it, but it's just be aware of it. And I think in the appendices I've given you the derivations of the method. Right, so with line SOR, okay, we solve a whole rows of points at a time. Okay. Still remains to be seen what's our best value for omega. Now for a tridiagonal system, okay, the optimal value of omega is given by this equation. And we've got, only thing which is undefined here is this row Tj. Okay. Now Tj is what we call an iteration matrix, and that's for the Jacobi method. Okay. And I'm just going to give it to you now. This is the iteration matrix for a Jacobi method. D, L, and U, right? A is your coefficient matrix. D is the square matrix, which is your main diagonal of A. L are your lower triangular elements of A, and U are your upper triangular elements of A. Okay. So this is kind of, you've got to trust me on this one. This is TJ. If you're interested in where that comes from, those of you doing ODEs in term 2, you'll be looking at that. Okay. If you got the notes for ODEs, the run cut aside, it's got the derivation of that in it. Okay, so in short, if we know what A is, we can calculate TJ. just by that matrix equation. Rho Tj is known as the spectral radius, and that's the largest eigenvalue of Tj. So we can calculate that, probably best off using a computer package to do that. Okay, so this rho Tj squared, you calculate Tj, you calculate the eigenvalues of Tj, and you take the largest one. Therefore, that will give you the optimum value of omega. Okay, to complicate things slightly, Tj depends upon omega. So you set an omega, calculate Tj, and then you get the optimum omega. But then that's changed Tj. Then you have to do it again. So again, we iterate to find the optimum value of omega. Okay, and in the example in the notes, it just how it happens to be omega is 1.036. Okay, same example. This is the one that took 33 iterations for the Jacobi method. Using line SOR only took 8 iterations. I think it was 13 for point SOR. Okay, so it's much, much more efficient. It's harder to actually calculate, but once you've sort of sorted that out and sorted the program out, it's a lot more efficient. Okay, so there are 4 methods there: Jacobi, Gauss-Seidel, point SOR, line SOR. Okay, each Jacobi is the easiest, then Gauss-Seidel, then SOR, then line SOR. But the point being is they have different convergence properties. You want the quickest solution. Now, when I do these, as you can see, even the Jacobi method just took just over 100th of a second to calculate. But that's for a very, very simple system. In practice, we have millions of nodes. Okay, it's not unusual for supercomputers to be working for days and weeks to calculate solutions to large systems. So we want to be as efficient as possible. So here are the iterations for the various methods. This CPU time is calculated or measured using tick and tock. These are just 2 MATLAB commands. Think of tick as starting a stopwatch, and tock is stopping a stopwatch. And then that will return how long the computer spent calculating. Okay, depending on what's going on in your background, if you've got music playing or you've got email open and things like that, your computer's having to do more work. So the CPU time will be different for different machines. You can run it once and then straight away run it again, you'll get a different CPU time. There's lots of things going on in the computer. So the best way to run this is run it several times and take the average of your CPU time. What if I was to do it on my computer and I was to get a CPU time and you were to do it on your computer, you'll get a different one again. Your computer may be more powerful than mine. So what we also tend to do is we normalize the CPU time for the slowest method. Okay, so the slowest method took 0.061 second. The line SOR method took 0.043 seconds. So if I divide 0.043 by 0.061, I get 0.27. So that means the line SOR method took 27% of the time that the Jacobi method took. And that should be similar for if you were to do it on your computer. Okay, so in short, line SOR is the best. More complicated to program, you have to use the Thomas algorithm. It's a bit more involved, but it's the best one. Point SOR is a good sort of compromise between speed and ease of use. Okay. Essentially, lots of number crunching. Lots of sort of, if you're doing it by hand, it's very tedious. That's why we don't do it by hand. Okay, any questions? That was quite complicated, especially the line SOR method. I'm not going to expect you to ever code up the line SOR method. Okay, so don't worry about that. Any assignment I give you will not have that in it. Okay. You should know the sort of the general method, but I'm not asking you to actually apply it. Okay. It is a bit involved. Right, you all okay? Is there any questions on that? No? Nobody want to ask me whether